So, uh, so for the first problem on the next assignment, we're gonna let A and B be non-empty sets and F from A to be a function. Show that F is one-to-one if and only if, remember, F inverse B, this, when I write it in this form, this is actually a set, right? F inverse B is all the stuff in A that happens to go to the number B, whatever B is, right? Show that if F is one-to-one, if and only if F inverse B, the number of elements in that set that go to B is less than or equal to one, right? Probably not a big surprise. Show that F is onto if and only if F inverse B is not the empty set for all B and B. And number C, well, what does bijection mean? It means one-to-one and onto. I bet you can put C together. Show that F is a bijection if and only if the cardinality of the set F inverse B is one for all B and B. Number two, let A be an infinite set, just infinite is all I demand, and let B be a subset. Number A, show that A is equivalent to a proper subset of A. And you may or may not have to use this. You may assume that any infinite set has a denumerable subset. So if I have the real numbers, it's got a denumerable subset. The natural numbers, it does. You may think this is obvious. This actually depends on something we have to do later called the accident choice. Yes.
What is a proper subset?
Okay, that's a great. A proper subset means a subset that's not the whole set in the first place, right? Like, for example, here are the students in the room. If I remove Megan, then what's left over is a proper subset. Number B, show that if A is denumerable and B is infinite, then B is equivalent to A. Right. Number three, let AK be a denumerable collection of non-empty countable sets. So in other words, each one of these AKs, they're not empty, but they're either finite or denumerable. Assume that each of these is finite. Show that this is finite. The product of these are finite by finding a formula for how many are in there and proving that it holds. What do you think might be a good proof technique for this? Can I induce you to give an answer? Probably induction. Show that each of these sets is denumerable. Show that if each of these is denumerable, then so is the product. The fact that this product is finite, there's only n of them is important. And
like if the cardinality is less than or equal to one, like is that not just M or like are there any elements like how can you have a
are you talking about 1A? What that means is the set of things in A that go to B. That's what F inverse B is. It's everything in A that goes to B. What that says is there's one or less, right?
Oh.
There might be zero.
oh okay.
Four, this is kind of a fun problem, I think. Let A and B be non-empty sets. Let capital F's of A be the set of functions from A to A. We've talked about a lot of this with functions from the reals to the reals. This is the set of all functions from A to A. Show that if A has more than one element, then the number of functions from A to A is greater than the number of elements of A. Now, let's kind of take the problem apart here. If A has only one element, there's only one function to one element to itself, right? So I did need bigger than one. If A has two elements, there's several functions from two elements to itself. Again, it's actually for finite sets A, this is pretty easy to show. In fact, you can count the functions. We do that later. The interesting part is, again, this is also true. This is like Cantor's theorem. This is true even if A is an infinite set. The number of functions is actually bigger than the size of the set. So here, these follow-ups, I think, perhaps a little bit easier. Now suppose that A and B are finite sets, suppose A is in, has n elements, B has n elements. How many functions from A to B are there? So do that count for me, count all the functions. And using this notation here, how many of these functions are one-to-one? So I want you to count the one-to-one functions, and all the functions in the one-to-one functions. You might ask why I didn't ask you to count the onto functions. That is a tougher problem. And you know, I don't pull punches on that sort of thing. So I didn't put it on your homework, but find it for onto as well for extra credit. You might find that it connects to one of the previous extra credit problems. Okay, any questions? Great question. Yes, I seem to be a little confused yesterday, didn't I? I will be out of my office a little bit after 11, got to leave a little early. I've got to go to a talk, but it's not, it turns out it's not the, the 18th, I'm gonna have this problem, so be aware of that. But I will be back, a little afternoon, as soon afternoon as I can. And I encourage you to get the homework done today, but, I've rolled the due date to Monday, just in case you need time. Okay, so I am going to talk about, and well, hopefully finish. I'm pretty sure I'll finish, one of my very favorite theorems. And I hope that it will be one of your very favorites soon, because it certainly is useful. The last theorem that we had, Cantor's theorem, is Cantor's theorem. So we had this, we proved this last time. I'm going to give you another theorem that might seem silly. I'll give you an application to this theorem. Cantor, right, so Cantor apparently unsatisfied with one solo, brought in Ginger Baker and Jack Bruce, formed a cream, and had this even better theorem. This looks at first like complete silliness, right? I mean, this is something clearly that we're used to with numbers, right? If I had two real numbers, A is less than B, they're equal, whatever. What does this say really? Well, this says, yeah, there exists one-to-one functions. F and A to B. That's what this means. And a one-to-one function P from B to A. That's what this means. Then there exists a packet. That's what the equality. Let me show you how of this theorem. Now, how many of you have finished this homework problem? Okay. How many of you have thought about it, right? I'm willing to bet that if you look back at your answer, you will find that this function that you built, because I asked you to build what, a one-to-one function. If you look back at your solution, you will see that this function is one-to-one, but if you look at it carefully, I bet you it's not on two. But you have a one-to-one function. Is there a one-to-one function here? Sure, right? Here's how I would do it. How about that? X goes to X comma, and I'll just put a random number in the second quarter. This function is one-to-one. That's easy to do. Cantor-Schroder-Bernstein says, you built this in the homework, this one's easy, there is some one-to-one and onto function from here to here. I challenge you to write that down, right? The one-to-one and onto function. Here's another example. How many of you have done the one-to-one function here? So actually, I believe I asked you to do a bijection for this, didn't I? I said, I want a bijection. It was complicated, wasn't it? I bet none of it was like really, it wasn't continuous, right? It was a bit of a mess. Watch this. The function that just takes everything to itself, that's a one-to-one function. It's not onto because I never pick up the end. Agreed? Can you think of a one-to-one function in the other direction? What would you describe?
So that reacts to itself, then you simplify something.
Oh, no, that's too much for my pea-sized little brain. Something easy. All I need is one-to-one. I don't need to onto it. Let's cut everything in half. Just like that. This is clearly one-to-one, right? Because if the half x equals a half of y, then x equals y. One-to-one function here, one-to-one function here. Cantor-Schroder-Bernstein says there exists a bijection. I didn't write it down, but it's out there, and that's all I have to know. So this thing is a nuclear weapon. I'll give you one more application before we actually prove this. I challenge you to write the bijection down. It can be done, but believe me, you don't want to do it. You don't want to, right? The inclusion function from C into Q is one-to-one. Just take every integer to itself over there. One-to-one, no way is it onto, right? Does anybody remember a function from Q into what did I say? Z? Okay. Actually, mine's going to the natural numbers. If I remember one-to-one function we did here. We can write any Q here as either, I'll write it either as 0 or as A over B, where the greatest common divisor of A and B is 1 and B is positive, right? Y'all remember when we did this one? Let me write Q equals A over B. Is, what did I do? Let's do it this way. Let's do 2A 3 to the B Yeah, is, A is greater than 0. We'll do 5 to the minus A, 7 to B, if A is less than 0. And 7 out of 309. If A. Y'all remember how we did that? This was 1-to-1 by the fundamental theorem of arithmetic. And in fact, it's not onto Z either. In fact, no negative comes out of this. And in fact, it doesn't even get all the natural numbers. 1-to-1 function from Z to Q, 1-to-1 function from Q to Z. Cantor-Schroder-Bernstein says there is a bijection. You might not be able to write it out nicely, but it's there. It's powerful. Yes.
So if we can just prove that like it's 1-to-1 one way and then 1-to-1 the other way, we can just state that there exists a bijection.
That's
Or
exactly what the
so we
theorem
don't have to,
says.
like, find the function.
Right,
find
so
the-
if I asked you to show this, I just walked up to you on the street and gave you those sets and show it's a bijection. There's a couple of things you might do. Number one, if you can figure out an easy way to do a bijection, then good, do that. But if you can't, it's often good to think, can I get a 1-to-1 map from here to here? And a 1-to-1 map from B to A? And if you could do both of those things fairly easily, which for some of these examples, it was really easy to do, much easier than writing down a bijection, then apply this theorem, right? By the way, I hate to break it, and anybody watching the video, which there better be some, I think that, for this homework, for the homework you're turning in on Monday, I want you to write down the bijections where I tell you, and the 1-to-ones where I tell you. I don't want you to apply this theorem until the next homework. Okay, this is a big one, and the proof is going to take a little while, which is probably not surprising, but because this is like a nuclear weapon, right? We're not going to build this like, stone spears and bear skins, right? This is going to be a little bit more here, but it's a fun proof. So let's get to it. Proof. And P from B to A. B, one-to-one functions. Okay, so let B inside B be the range of F, and C inside A be the range G. Okay, so this is really kind of not part of my proof, but I'm going to write some stuff up here. Hopefully it's visual aids to help you along with the process. So here's what we have. We have two 1-to-1 functions. Say from A to B. Okay, so what happens to A? I'm going to divide B up into so F goes from A, but everything over here, it's 1-to-1, but it all ends up over in the range of F, right? Maybe there's this no person's land where, there's nothing is covered, right? And by the same token, this is F. We also have G that goes in the other direction. Call it C, branch G. And even though this is 1-to-1, stuff in B doesn't cover it. It all ends up down in here, right? Everybody kind of get the picture here. This is 1-to-1, so no two different points go to the same point over here, but you've got this part that's uncovered, right? And that's the problem that we're trying to avoid. In fact, let me make that kind of clear here. if B take away D is empty, this means F is onto. And we're done. Right? That is to say, if B minus D is empty, that means D is this whole thing. That means that the range of D is all of B, and F is not only one to one, it's onto. There's our projection, we're done. Everybody okay with that? We need to tackle the problematic case where B minus D is not empty. So so how are we gonna deal with this? B minus D being not empty, we need to take care of this. So there are some points here that are not covered. They're very sad, they're lonely because they weren't covered by this function, right? So we are going to define a special type of function. T from the natural numbers to A union B, which I will affectionately call a train. I'm going to use this terminology, this special function. But let me point out that I'm going to call T a train function. And I'm going to have maybe lots and lots of trains. There's lots and lots of train stations here. So here's how I'm going to define the train. Might be a good idea to keep this over here. I'm going to let T of one equal B. So I'll start my train here at some B here. And I'm defining this sort of induction, right? So I start off here. T of one is here. This is the first part of the train station. I start my train with something that's not covered by the function F, right? So I look in this no person's land, I find a point that's not here, and I start my train. Now, I'm going to write the inductive and kind of explain to you what happens here. From this, we let Tn plus one be GTN if En is in B, and we're going to let En plus one equal F Tn if Tn is in A. Okay, that may look confusing, but it's really a simple idea, right? Pick one of the points in your no person's land. This is the first stop. This is the first station on the train. How do we define T2? Well, T1 is in B, so T2 is going to be what G does. So we just take this and see what G does to it. And by the way, this is T2. By the way, why did I draw it here? Because remember, what am I doing? I'm taking this thing and I'm doing G to it. So it has to end up in the range of G. Agreed? It can't end up here. It's got to end up in the range of G. Now I am going to do T3. And what does this mean? I just apply F to it. G notice that since I'm doing the function f to something that's already in A, then I have to go into the range. I have to go south of the border, if you will, right? And then we go to T4. And then T5, etc. And this train just keeps, now, after that first step, when I go here, it just goes back and forth between the range. And it just, we run this train. Everybody okay with that? So that's the idea behind the train. And let me point out that it's not just this one train. If I've got any other points here, I start a train here. So there's a train that starts at the station for every point that's north of the border. Yes.
Is T3 F of T2?
Actually, it certainly is. Very good. Thank you very much. Right. F goes this way, G goes this way. Okay. So basically what happens is you start with any point here that's not in the range of F, and you start a train station and go south of the border and just keeps going back and forth as I hit it right now. Okay. How is this going to help us? Well, I am now going to let write this down. Each being in B minus E is made T1 for some train. So again, I might have lots of trains running back and forth. Now I want W to be set of X in A such that X is a term in some train. I'm going to look at the set of everything in A that is part of a train, right? So for example, in my picture here, T4, that's an element of A, that's part of a train. T2 is part of a train, right? T6 will be, T8, et cetera, et cetera. Do I agree with that? Notice, what can you observe about W? Everything that's part of the train must be south of the border, right? Because to be part of the train, it has to come from over here, right? So it has to be in the range of G. So it has to be, so everything, so notice that W is contained in C. Right, okay with it? So if X is W, then X is in range G, and more than this, let me be more specific. I'm not done yet. If X is part of a train, what can you say about it, right? Do you notice a pattern for what part of the train? Like, for example, could X be T3? No, it has to be an even stop on the train, right? Y'all notice the odd. So we always start over here in B, right? And so the odd parts of the train are in B, and the even parts of the train are over in A. Right? So in fact, X is T2N. Natural numbers. Okay, so Listen, we need to find how much. Maybe y'all can help me. I'm gonna call this projection H. A, B. Anybody wanna take a guess? Let me break it up to you. And so there was a point of me defining this W here. I'm gonna define this one in two cases. One, when X is not part of the train. Number two, when X is part of the train. What do you suppose? What if X is not part of the train? How can I push? Suppose you have something that's not part of this train. Notice that this would apply to everything in the northern hemisphere here, right? Because none of these things that are not in the range of G can be in the train. Well, how can I push that over to B?
It started, right?
Well, it can't start a train because I've declared that all trains have to start over. Well, remember, we have our functions f and g in the first place. Right? I'm going to say that if X is not part of a train, you know what I'm going to do? I'm just going to use F. And that's going to go over there. So I'm just going to use F if it's not part of a train. What if it is part of a train? Like, for example, this one right here. That's part of a train. What might I send T2 to? Well, you could send it to T3, but see, here's the problem. I'm worried because T3 is actually in the range of F. So what if I sent something here that also went to T3, right?
Right, exactly.
Run the train backwards, right? And this is cool, right? So T2, where did T2 come from? It came from over here. And notice that this comes from a place that can't be touched by one of these over here. So let's do this. Let me write it this way. If X is in W, just run the train backwards one step. Well, okay. Now, there's the answer. That is how you build the function from A to B. But still got some stuff to do, right? Because just because I wrote it down, that don't make it right. So let's figure out why this works. So, first of all, I always have to worry about whether this thing I built is a function, right? What do we have to do? I'm going to do this a little bit informally, but what do we need? We need for every X, we need to give one and only one output, right? Well, let me point out that if X is not in W, then there's only one output that you can get, f of X, because F is a function, right? Do I agree with that? What if X is not, what if X is in W? G inverse X. How do I know that that is a unique output? Remember, what do we know about the function G? We know that G is 1 to 1, right? The inverse of it actually is a relation, right? And that, well, actually, we know that, right, this inverse relation actually is a function, right? Because of the fact that G is 1 to 1, right? So this gives, so once I have the X here, this is an X over here. that's actually in the range of G, and since G is 1 to 1, there's only one place that it can go back, right? Because 1 to 1 is, yes,
So are you able to say that h of x is a function because f of x is a function because g of x is 1 to 1 g inverse of x is a function?
H of X is a function because F is a function and because G is 1 to 1.
Yeah.
Right. Everybody okay? So, what part? F is a function and G is 1 to 1. I've got to convince myself now that this is in fact a bijection. So let's do 1 to 1 first. Show that H is 1 to 1. Suppose X and Y are in A and H of X equals H of Y. What cases do I need to consider?
That's why or not.
Right, so I think I've sort of got 3 cases, right? X and Y are both not in W, so they're using this rule. X and Y are both in W, so they're using this rule. And then the mix, right? One of them uses this rule, one of them uses that. It turns out using the mixed rule doesn't work, right? And I'll prove that to you right away. So, case 1, let's suppose that, X is in so let's suppose that X is not in W and Y is in W. What does this mean? H of X equals H of Y means that F of X equals G of Y. I'm sorry, that would be G inverse of Y. Right, because X uses this rule and Y uses this rule. Everybody okay with that? So in particular, Y is equal to G of F of X. All right, just composing both sides of that, or composing both sides of this with G. Since Y is in W, that means that it's an element of train. Right? Because remember, Y is in W, that's our assumption. And so what does it mean to live in W? It means it's term of some train. So Y is actually, since Y is in A, it must be an even stop on this train. Everybody agree with that? So if you look at so Y is the 2 stop. Let's look at the previous stop on the train. The previous stop on the train must be F of X. And let me justify this for you. This is because G of 2n T2n minus 1 is equal to T2n, because that's the way the train works, right? And this is equal to T2n, which equals Y, which equals G of F of X. So G of F of X equals G of T2n minus 1, which implies that F of X equals T2n minus 1. So I've sort of justified this right here. By the way, how did I pass from this step to that?
Take both sides as a function of G inverse.
Well, so what I'm saying is, I wouldn't go that far. Well, I would say this, G of Bill is equal to G of Fred. And I've concluded from that Fred equals Bill.
Since G is one to one.
Because G is one. Right. Because G is one. Everybody okay? Okay, so. If. So, let me kind of figure here. So f of x equals t 2n minus t. If n equals 1, f of x is equal to t of 1. So we know that f of x is t2n minus 1. If you take n equals 1, that would mean that f of x is t1. So see, remember how we chose t1? All my t1s, all my starting points of train can't be in the range. So that's a contradiction. So, okay, that can't happen. It's got to be something bigger. But if n is greater than or equal to 2, then t of 2n minus 2 is equal to x, since f of x equals t of 2n minus 2. I'm sorry, 1. Right? And so again, we're using sort of oneness here of f to give us this. Hence, is a function. So x is in there. And this is a contradiction. Because what this shows is x has to be a term on the front. Okay, what have we done so far? Well, we've shown that case 1 can't hold, right? So you've got to pair up on the rules, right? So in other words, when I go back to h of x equal h of y, they can't use different rules because I got this contradiction that x is a term on a train, which it can't be. Case 2, x and y are in not in W. Now it's easy. H of x equals h of y implies f of x equals f of y. Because that's the way that h is defined for that first rule, which implies x equals y as f. So now we've got that. Case 3, x, y not in W. In this case, oh, let's see if I can get it. In this case, x, y is in W. In this case, h of x equals h of y, implies that G inverse X equals G inverse Y, which implies X equals Y by composing G. And there you go. So H remains, or I should say is one of them. Okay, the onto, I think is a little bit easier. In fact, this is kind of set up to be onto. Unfortunately, we dodged probably 1-to-1. Suppose B is in B, need to show there exists A and A such that H of A equals B. Case 1. Okay, so I walk up to you on the street and give you a B. You need to find me an A such that H of A is B. So case 1, look at G of B. Suppose that G of B is in W. So in other words, it's part of a triangle. Call for convenience, G of B, X. H of X, well, X is GB, which is in W. So that means I have to use this rule, right? So H of X is G inverse X, which is G inverse G of X. I'm sorry, which is G inverse G of B, which is B. And there we go. That was an easy part of the onto. On the other hand, what if G of B is not in X? Or I'm sorry, not in W? In this case, G of B, or in this case, B is in the range of F. Because if not, then B is in B minus A. So if B is not in the range of F, it has to be in the northern hemisphere, if you will, of that drawing. And is T1 for some frame T. And so B equals T1 and G of B equals G of T1 equals T2, which is in W, which is a contradiction. Because we've assumed that G of B is not in W. So there exists X in A such that F of the X is equal to B. Because, as we've said, B is in the range of F, so I can find an X in A such that F of X equals B. If X is an element of a train that's in W, then F of X and G of F of X equals G of B, but in W, which is a contradiction. So X is not in W, and H of X must use this rule. It's F of X, which is B, and onto and we totally vanquished it. So there is proof at 8:49. Perfect. Any questions? Okay, put that in your pipe and smoke it. It's a lot of smoke. So think about that. Let me know if you've got any questions. Try to get the homework done today, but you've got until 2 o'clock on Monday if you're in the spot. I encourage you to be at the math club today because we've got a visitor from Spelman College who's going to talk about energy choice games. Looks like a lot of fun. Other than that, y'all have a good weekend.